In this section, we'll be dealing with mathematical models of control systems. We'll be talking about why we need mathematical models and what is actually a mathematical model. In a control system, our objective is to obtain a desired output from a physical system by controlling our input to that system. We know that our aim when we give an input is to get a desired output. So you know that in a control system you can get that desired output by providing a particular input. But the main question is, how do we know what input should be given to get the response that we want from the system? That is the driving question. What should I give to get the desired output from that system? For that, I need to know what is happening inside the system and how that system responds to particular inputs. For this, let's take an analogy. Let's compare a physical system with a human being. Just like how different human beings respond differently to the same input, different systems also respond differently to the same input. So if a particular person gets shouted at, one person might become sad, the other person might retaliate. The input here is being shouted at, that is not changing, but the way the human beings respond is different. One of them became sad, one of them kept quiet, whereas the other one retaliated and shouted back. Similarly, for different systems, it is seen that although the same input is given, different systems provide different responses. Now, why do different human beings respond differently to the same input? Due to the difference in their character. That is how they have been brought up and that is how their character has developed. That is why they respond differently to the same input. Similarly, different systems have different characteristics and hence behave differently. So the next question becomes, how to know their characteristics? How do we know how they will respond to a particular input? By looking at the differential equations that govern them. So just like how a human being has a particular character, every system has a set of differential equations that govern them, and by looking at the differential equations of that system we can identify how it will respond to a particular input and what output will be produced. And so we can safely say that if we know the governing differential equations of a system, we can actually predict how they are going to respond to a particular input, or in other words, we know the characteristics of that system. So to know the characteristics of the system, the only thing that you have to do is look into their governing differential equations. Now, a particular system will not have just one differential equation, it will have a set of differential equations depending on different situations. By using all of the differential equations that govern a physical system, we can create a mathematical model for the physical system. A mathematical model is the set of differential equations. That set of differential equations actually represent the physical system that we are trying to understand. But why create a mathematical model? So that we can predict what output will it give if we give a specific input without actually applying that to the physical system and waiting for its output or response. So if we create a mathematical model, what we can do is we can give certain inputs, and when you substitute those inputs into the differential equation, it will produce an output which will be equivalent to the actual output that the physical system will give if we give that input. So without actually applying it to the physical system and waiting for the output, we can actually test out different sets of input conditions to get a particular output. And what is happening? We give a particular input and the differential equations actually transform this input to the corresponding output. So we are actually transforming the input through the differential equations into an output, and that is what is actually happening in a physical system. When we give an input, by the set of differential equations that govern them, that transforms the input and produce a corresponding output. Now if we know how the inputs are being transformed to get the output, that is by knowing the differential equations, we can actually reverse engineer the desired output we want to get the input we need to apply. So what we do is, if we take the set of differential equations, we give what output we want, and we find out what input should be given so that the corresponding output or the desired output is obtained, which was our aim after all. That is what we wanted. We wanted to know what input should we give so that it produces the desired output. So it is by creating a mathematical model and substituting the values, we can find out what input should be given to produce a desired output. Now this is the basis of using mathematical models to study physical systems. In this section, we'll be looking into the linear and time invariant systems. Now, LTI systems or linear and time invariant systems are a class of systems that we are interested in because the transfer function that we'll be using is based on LTI systems. So, before going on to transfer functions, it is a good idea to know what LTI systems actually mean. Now, these are systems like any other system which respond in a particular way when subjected to an arbitrary input. Now, all LTI systems have the following three characteristics: homogeneity, superposition, which is also known as additivity, and time invariance. Here, homogeneity and superposition are two criteria which describes the linearity of an LTI system. What it means is that if a system satisfies both homogeneity and superposition, only then can you call that system as a linear system. Now we'll go on to understand in detail what homogeneity, superposition and time invariance means. For this, let's look at a diagram. What I'm going to do is I'm going to draw an LTI system. Let's name this, let this be an LTI system. And LTI system, we don't know what is actually inside. Let's consider this as a black box. And what I'm going to do is I'm going to input a value, say x of t, into that. And since this is a system, it will produce an output, and let that output be y1 of t. Okay. Now, if this system obeys the principle of homogeneity, it means that if I scale the input by a factor of a, which means that if I multiply x of t with a scalar value of a, or which we can write it as a x of t, okay, a into x of t, and measure the output of LTI. Now once you input a into x of t, let us assume that as an entirely new input. Let the input now be, instead of y1 of t, let it be y2 of t. Okay. Now what will be y2 of t if you input a into x1 of t? It is seen that if it obeys homogeneity, then y2 of t will be equal to a into y1 of t. Now if a system exhibits this property, then it is known as a system which obeys homogeneity. Now what is a practical example of this? Practical example will be, instead of a, you just imagine as 2. So if there is an input, you give an input to an LTI system and it produces an output. Now you double the input, and if the output is seen to double, then you can say that that system obeys homogeneity. Now that is what is being mentioned here. Let us assume that we have an LTI system which is fed with x of t, and let the output measured be y1 of t. Then the principle of homogeneity states that if we scale the input by a factor a, means now the input is a into x of t, and measure the output, say y2 of t, then we can say that y2 of t is equal to a into y1 of t. Or in other words, if we say double the original input, the new output will be double of the original output. For simplicity, let's consider a resistor of 10 ohm as an LTI system. We are just taking a resistor of 10 ohm and let that input to that resistor be the current that is being sent through the resistor, and the output is the voltage that is developed across the resistor. Now if we input 1 amperes, and since we know the resistance value is 10 ohm, we'll know that the output that will be developed across the resistor will be 10 volt. Now if we double the original input, that is, the new input is 2 amperes, which is 2 into 1 ampere, or a scale by 2, we know that output will be 20 volt, which is actually 2 times the original output. Thus we can say that a resistor satisfies the homogeneity principle. Next we go on to superposition principle. Again, let us assume that we have an LTI system which is fed with x1 of t, and let the output be measured as y1 of t. Now if we feed the same LTI system with x2 of t, and let the output measured be y2 of t. So we are taking a single LTI system and we are feeding in x1 of t, and we are measuring the output, and let that output be y1 of t, and to the same system we are feeding x2 of t, and then we are measuring the output, and that is y2 of t. Now the principle of superposition states that if we now feed the system with x of t, a new input which is actually the summation of the initial inputs, the two inputs. So x of t, the new input, is actually x1 of t plus x2 of t, and then we measure the new output y of t, and if the output is actually the summation of the earlier outputs, then that system satisfies superposition. Now we'll take the example of the resistor itself. Now we know if we input a current of 1 ampere, because the resistance value was 10 ohm, the output will be 10 volt. Now if we input 4 amperes, the output will be 40 volt. Now what we are doing is we are inputting a current of 5 amperes, which is actually the sum of 1 amperes plus 4 amperes. And we measure the output. We know that output will be 50 volt, but that 50 volt can be obtained by simply adding the previous outputs, that is 10 volt plus 40 volt. And since it satisfies this condition, you can say that it obeys the superposition principle. Now since it satisfies these two principles, that is both homogeneity as well as superposition is being satisfied, you can say that a resistor is a linear system, or in general, if any system satisfies both superposition as well as homogeneity principles, then that system can be called as a linear system. Now once it's a linear system, the remaining thing is time invariance. Now what do you mean by time invariance? It refers to the system behaving the same regardless of when in time the action takes place. Now it might sound slightly difficult to understand, but it's very simple. For example, if we throw a ball at a wall with same force and angle at 4 p.m. or 5 p.m, the way it bounces back will be the same. It doesn't matter at what time that we do. As long as you maintain the input trajectory as well as a force, the way it will bounce will be almost the same. So it does not depend upon the output of the system, does not depend on at what time you are giving the input. Now if we generalize it, if x of t is the way we throw the ball at 5 p.m. and y of t was the way it bounced back, we can say that if the ball was thrown at 4 p.m. is x t minus a, where t is the time at which it is being thrown, and we are reducing 1 hour, because from 5 p.m. if you reduce 1 hour you get 4 p.m. So to get the input at 4 p.m. what we did was we took the input at 5 p.m. and reduced 1 hour. So the input has been changed from x of t to x of t minus a. The output was yt minus a, and if that gets satisfied, that means that the system is time invariant. Now if we take the example of resistor again, if we supply it with 1 ampere at 1 p.m. or 2 p.m, the output will be 10 volt. It does not depend upon the time at which you are giving the input. So any system which obeys these three principles belong to the class of LTI systems.